Okay. So now we basically want to we're going to find the real numbers to be rational cuts. So a Dedekind cut is, let's say, AB. Is it just a cut? Such that A has no greatest element. Okay, we just have a quick proposition, which just says every Dedekind cut is either a gap or a rational cut. Either C is a rational cut or a gap. And this is just the proof of this is just to kind of use the definition of everything. So proof. Okay, by definition of Dedekind cut, A has no greatest element. Okay. If B has no least element, then C is a gap. That's the definition of a gap. It's just a cut where A has no greatest element, B has no least element. It is just a definition. Okay. Otherwise, if Q and B is the least element of B, then we claim two things. One is that B is just a set of rational numbers bigger than Q. And two, we claim that A is just a set of rational numbers less than Q. Okay, so let's prove the first one first. Well, Q is the least element of B. So for all R in B, R is greater than or equal to Q. That's just the definition of least element. Of B. Okay, so what that tells us is that B is a subset of this set. Forgot to move up. Okay, and we want to show these two sets are equal. Well, now suppose that we have some rational number R bigger than or equal to Q that's not in B. Okay, then R is in A. Well, since A union B is the rational numbers. Okay, but now every element of B is less than every element of A is less than every element of B. So in particular, R is less than Q, since R is in A and Q is in B. But by hypothesis, R is bigger than or equal to Q, which is a contradiction. Okay, so there's no rational number that's not in B that's bigger than or equal to Q. Therefore, B equals the rational number is bigger than or equal to Q. And now A is just a complement of B relative to the rationals. And it's just to remember that every number that's not bigger than or equal to Q is less than Q. So now, since A union B equals Q, A intersect B is the empty set, A is just the rationals that are not bigger than or equal to Q. That's just the rationals that are less than Q as required. So in this case, C is the rational cut CQ. Okay, so we've shown that every Dedekind cut is either a rational cut or a gap. That's what we wanted. Okay. Okay, and now we define the set of real numbers to be the cut C such that Dedekind cut. Okay. I guess because this is set theory, we should write a brief explanation as to why, so each C is like an ordered pair, and A and B are both subsets. So this is an element of the power set of the rationals cross the power set of the rationals. So it's a power set of the rationals, and then that's a set. And so we can take the Cartesian product of these two sets and get a set. Okay. Okay, and that's where the Dedekind cut, all the Dedekind, then we can apply the axiom schema of comprehension, Okay, so the set of real numbers is really a set. Okay. Okay, and now we want to okay, so this is supposed to be real numbers. So what would be is that we like defining addition and multiplication was kind of natural. But what we're going to do for the real numbers is we're going to prove like the real numbers have a natural way to order them. Because each real number is like each real number is like a way to cut this. So here might be this might be the real number A, and this might be the real number B, and A is going to be less than B because this half like covers up this half. This half of the B cut is more than this half of the A cut. Okay, so let C1 and C2 be real numbers. We define if and only if A1 is strictly contained and not equal to A2, where C1 is the cut A1B, A1B. Okay. Which says less than or equal to on R. Not only that, it's a linear order. So this is 1, 2, 3. And P and Q are rational numbers. Then the rational cut CP is less than or equal to the rational. Any inequality that you get from rational numbers still holds true in the real numbers. Okay. Okay, so actually, these first two are not too tricky. So maybe I'll just do the granted that less than or equal to on the real numbers order, given that. And then this is not too hard as well. Okay. So let's do that. Okay, proof. So this part is going to be omitted. It's not bad. And the real numbers. And we need to show that either C1 equals C2, C1 is less than C2, or C2 is less than C1. Okay, so we're going to write C1 and C2 equals A2, B2. Okay, so either A1 is a subset of A2, by okay, that'll be good enough for us for now. Okay, the other case is that A1 is not a subset of A2, so that means there exists, let's say, a rational number. Then Q is in B2. That's because A2 union B2 is the rationals, and A1, A2 intersect B2 is the empty set. Okay, so Q is in B2, so every element of A2 is less than Q. For all R in A2, R is less than Q. Okay, so now we have A2 is contained in this set of all R such that R is contained in A1, so that A2 is contained in. And there's a lot of ways to see this. So this is true, and we want to let R be less than Q. If R is in B1, then Q is less than R. Okay. So you can't have R is less than Q and Q is less than R for rational numbers. This would mean that R is less than R. This is impossible. R is not in B1, so R has to be in A1. So every number less than Q is a subset of A1. Okay, so A2 is contained in A1. So therefore, C2 is less than or equal to C1. Okay, that means for any two real numbers, either C1 and C2, either C1 is less than or equal to C2 or C2 is less than the second part. Oh yeah, that shows that less than or equal to is a linear order on the real numbers. And now we just need to show that if P is less than Q, then CQ. Okay. Okay, so now let P, suppose P is less than Q, then AP, which is just the rational numbers that are less than P. Well, every rational number that's less than P is also less than Q by transitivity. since if R is less than Q. Okay. And this is just a Q. So by definition of less than or equal to, CP is less than CQ. Well, but to show not equal to, well, because Q is not in AP, because Q is not less than P. Or rather, no, that's, we can say that P is in AQ, but not AP. Less than CQ. Okay. So now we have a set which is like total, which is numbers as a subset, and like it extends the order on the rational numbers, rationals, and some which correspond to gaps. Okay. Which is kind of like the starting point of like doing analysis. Okay. I'm not sure if we have, so theorem. Let C be a subset of the real numbers such that it's non-empty for all C in C, or I'll say there exists C star, okay. Then C has a least upper bound. So every non-upper bound. Okay. Okay. So let's think about what it should be. Define A naught just to be like we can kind of think about it. I guess we can try and draw a picture. Okay. We'd have a bunch of cuts in the rational numbers. Okay. We have a bunch of cuts like this. So to get the biggest cut, let's just take the union. Let's take all the unions of all the A's coming from C. So the rational numbers X such that C equals AB in our subset. That'll be A naught. And define B naught to be those rational numbers. Okay, so automatically we get that A0 intersect B0 is the empty set and automatic rationals. We also want to show that A0 has no greatest element. We want to show that every, okay, then we'll have a Dedekind cut. Then we want to show that this cut A of the least upper bound for C. Okay, obviously I can't do all of that in 3 minutes, but I'll just, okay, so we need, the first thing is to show that for all A and A naught and B naught, A is less than B. 2, A naught has no greatest element. Okay, and then once we do that, then that'll tell us that C0 is a real number. Okay. The fourth thing is that if C for C, then C naught less than C star, and 5, C less than or equal to C naught for all things. That'll prove that this C naught is the least upper bound of by construction. So that's the easiest one. This is also not too bad. To me, these two are the hard. We'll kind of try and finish this on Wednesday anyways. Okay. Okay, I guess if you're still with me, thank you very much. Yep, that's it. Okay, thank you. Okay, bye.